advanced electric drives, and we are discussing the realization of power converter and the control of the DC motor drive. So we have discussed a lot about what we mean by buck converter, boost converter, and how the power flow is happening. So all these things we have discussed in detail, and what we have seen that finally what we have in a system basically power flowing between a voltage source and a current source or vice versa. So based on which quantity is getting reduced or which quantity is getting boosted, we define the type of converter as buck or boost. Then we may have, let's say, a combination of buck and boost and something called as buck boost converter or flyback converter. These things can be realized, and even more complex converters. Now, everything in all these converter involves the SPDT switch, and that we have seen that it can be realized by using one of the practical switches which are available, say diode or BJT or MOSFET or IGBT. So based on what voltage blocking we need and what current flow we need, based on that we can decide which switch can be placed in the SPDT arrangement. So we have seen that for the multi quadrant operation, we may have composite switch kind of arrangement where two or more switches can be connected in either anti-parallel mode or something called as anti-series mode. And if two such combinations are connected together, we can have all four quadrant operation. So these are some of the things which we can be useful in realizing the power converter. And as we saw in the yesterday's class that we have buck converters. So PT1 and PT2, these switches can be defined with what is the direction of flow, what is required, and what is the direction of voltage, what we need to block, or the polarity of voltage, what we need to block. So based on that, we can decide which device can come in that place. And so finally, we have some realization like this. Similarly, for boost converter also, we can have the arrangement given as this. So anything further if you want, it could be a combination of these two. Moreover, if you want to have bidirectional power flow instead of unidirectional, then basically what we need that these switches should have capability to take negative current as well. That means current in both the direction, positive as well as negative. So we can have a composite switch kept at both the places, and this is sometimes known as the synchronous buck converter, so which allows the current to go positive as well as negative direction. So we have bidirectional power flow. So up to this point we have discussed like how to realize. Now slowly we are moving into how to control the power converter. So it is not just important to realize, but it is important to control it as well. So we are trying to first model like what do we mean by, let's say, power converter mathematically. So what we have seen that first how we are operating the gate of any active switch. Let's say MOSFET is there. How will you trigger the MOSFET for a given T on, T off, and for a given V output voltage, let's say. So how do we realize that? So we can have a reference voltage getting compared against a ramp signal. So the maximum value of ramp signal could be 1, and the Vref can vary something between 0 and 1. So based on this position, wherever it is intersecting this ramp, so whenever it is more than this ramp, we can turn on the gate for the active switch, and whenever this ramp is more than this Vref signal, we can turn off. So on an average, this is depicting the on and off operation of our circuit. So whenever the gate is on, which means, let's say for buck converter we are talking about, so we have VG applied at the pole voltage, and then when the gate is off, so that means diode is conducting, we have 0 voltage applied at the pole voltage. So on an average, we are getting something called as DVG, which is the output voltage that we know. Now this can be related to our control signal. So by changing Vref, we will be able to change the output without disturbing any other thing. So we can fix the frequency of this ramp, what is running over there, which will fix our switching time period TS. And based on the position of this reference signal, the T on duration will change, or the width of this pulse will change. And so we can have the output which is related to the reference signal like this. So we have related our V reference signal to the T on and T off times, and it is coming something like this for the condition that Vp max is equal to 1. So then our V0 is very much related to the input signal Vref as this. So it is nothing but Vg or the DC voltage multiplied by the reference. So this is kind of gain that this converter is giving to our input signal. Now, the phenomena what we are observing over here, that changing the pulse width is changing the output voltage. So this is what is known as the pulse width modulation, which will be used for DC to AC converters as well. So this is the concept which is used invariably everywhere. By changing the width of this pulse, we are not changing the duration of this switching frequency or switching period, we are not changing, but we are only changing the duration of this pulse for which it is high. So then what we are doing, basically we are modulating the width of this pulse, and that is what is popularly known as PWM. So we will see in a more elaborate manner for DC to AC converters, but just to understand what we are doing, we have given an example over here. Now this is something, the model of our converter. So we have basically the input voltage coming, and that is multiplied by the gain VDC, and then our output is coming out. So this is mathematical model. Some equation or function we can have to define that. Now we have moved towards the control of the separately excited DC motor. This is what ultimately we are targeting. So when we say control, I am not suggesting that whether it should be open loop or closed loop control. We will see one by one what is happening. So first, let us say if you just want to operate it in open loop mode, you can have some DC voltage applied to the power converter, and you can give some V reference to the ramp, and this kind of arrangement you can have to compare and generate the output for this power converter and connect the DC motor. And without any control, it can run. There is no problem in that. So based on your V reference voltage, V reference value, your omega will change. So mostly it is almost proportional, and if you want to increase the omega, you need to increase the voltage. If you want to reduce omega, you need to reduce V reference. So that's the open loop control, and it does not say anything about how fast or how good this control would be. It may be very good, it may be very bad, depending on what application you are putting it into. So we will discuss about the quality of all this today, tomorrow, during these two classes. So let us understand a little bit more about the system. So open loop we can operate, but still we have no understanding about what is the behavior of the system and how to define the performance of the system. So then here also we are doing the mathematical modeling of this separately excited DC motor. So electrical equation we have written where this back EMF can be written in terms of omega. And then the mechanical equation we have written where the electromagnetic torque can be written in terms of Ia. So we have some kind of block diagram arrangement for this separately excited DC motor. We have VA, the armature voltage, then EB is subtracted from that, and then given to this first order system RA plus SLA, and then the armature current is generated, which is multiplied by the constant, and torque is generated, then the load torque is subtracted, again first order mechanical system which is generating omega. So of course the omega is responsible for generation of EB. So that's why we have this feedback loop kind of thing coming over here. So this is for the motor. Now if we have the converter also, this can be extended to this part as well. So basically V reference generating this VA through this DC voltage VG. So this we can say is block diagram, or you can say open loop block diagram for power converter plus the separately excited DC motor. Correct? This is fine, right? Up to this there is no problem. Fine, everyone?
Yes, sir.
I have covered a lot of content in the last class, so that's why I'm keeping it little bit slow today. Okay, so wherever you have doubt, because you need to join with me, no, to understand this thing. You need to do it yourself as well. So now what we are basically trying to understand first is why do we need any closed loop control? What is the need for closed loop control? This is what we will discuss today. And then what should be done to achieve the closed loop control for the separately excited DC motor. So here, first let us discuss. Now, ultimately, if you see, okay, I'll go back to that block diagram. Maybe it is easier to see from here. See, ultimately what you have some input given over here. And you have some output over here, right? So in between, whatever is happening is basically the you can say dynamics of the system or the response of the system, whatever you want to call. This is all happening. So in general, we can say this is something like a transfer function GS. Okay, I hope you are a little bit aware about what transfer function is and know how to define it, right? Correct, right?
Yes, sir.
Yes, sir.
So some basic control, all the MTech must have done the advanced linear control and all. And those who are doing direct PhD, they also must have done some control class. So I'm taking this assumption that you have some understanding about this. The rest we will develop here. So now what we have basically, this complete thing, if I write here, this is what it represents. We have some input given and some output is generated here. Isn't it? Now, omega is basically Vref times of GS. Now, what are the problems associated if you want to operate this system in open loop mode? Any system. Let's say here we have this motor, but it could be anything. GS could be any general system. So what problems do we have? Okay, can you state one or two problems at least?
Sir, system could be unstable, like the poles might lie on the right hand plane.
Okay, could be unstable, but we still don't know what is definition of unstable. So a more, let's say, general understanding about this thing could be that we are trying to generate speed on basis of some voltage. Okay, and the correlation is only the understanding what we have. The system doesn't know what is the relation between this omega and Vref. You apply some voltage, some reference, and some omega is generated. So there is no guarantee that whatever omega you want to generate, you will be able to generate with this Vref. You understand my point? System doesn't know how omega and Vref are related. It is you who are deciding that how it is going to run. You may apply some voltage, but whatever you are expecting here may not be generated. Correct, due to maybe some voltage drop here or some change in parameters over here. Many reasons could be there. So very strong reason could be that parameter variation could cause the change in performance or change in the output for the system. Correct? Any doubt in this? This may happen. It's a very, very common thing. The system gets heated up, resistance changes, and a lot of other things are there. The third possibility could be that you are feeding something is generated, it is fine. But what if some noise is coming on this system? Let's say anywhere the noise can go, either on the output or somewhere in the system itself. So this noise may disturb your output, which you wouldn't know from the VRF point of view. You are simply giving a reference. So in short, whatever we are trying to generate, we may not be able to because we don't know what is the direct relation between the output and input. It is related through this function that is physically available. But in the system or in the control, we don't have any relation between this and this. So somehow what we need to do, we need to nullify the impact of parameter variation. This gain or this transfer function, whatever is coming, somehow we need to nullify this impact. So in short, what we are trying to do, if we are generating a speed, the reference should be speed. and the output should be speed. It should not be something like voltage reference and speed output. You understand my point? Generating speed from speed reference is reasonable. Yes, somewhere you can track whether it is matching, not matching, some error is there, but you cannot compare speed with voltage. You cannot say 5 volts is equal to some 1000 RPM. You cannot say that. But I can say yes, 1000 RPM is equal to 1000 RPM or not. You understand my point? So somewhere we should have a system like this. So what simple method could be there? You simply take inverse of this transfer function, say G inverse S, and you feed your reference speed to this. So if G is generating omega with Vref input, what this will generate? You understood my question? What will be the output of this system?
Sir, V reference.
V reference.
V reference. So now we have, let us say, a correlation between the speed and V reference. And what we do, we put this system with our actual system. So now the situation is similar to this. You are feeding speed reference, you are getting speed output. So you have some measure of whether it is going good or bad. Understanding my point? You understand the point? So effectively
Yes,
what
sir.
is there that you have made this whole thing as unity. You are feeding speed, you are getting speed. So you have cancelled all the impacts of whatever this system may cause. Any delay or any disturbance or anything. Understanding my point? So this is the most primitive thing what can be done. But there are hundreds of problems with this solution. First of all, it is not always possible to model GS perfectly. And then getting G inverse is always difficult. And it may not be possible to implement G inverse always for a given GS. Correct? So theoretically this is fine, this solution is fine, but practically this may not be feasible. We may not be able to get a correct representation, most accurate representation of any system. It is always approximate. And secondly, taking inverse and then implementing that may be further difficult. So then what is the solution? And the other problem, the noise issue and the parameter variation, this also is not solved. If let us say this changes its parameter, whatever you model over here, the value is not going to match. Or if there is some noise coming somewhere in this system, whatever you do, you are not going to solve this. So always this kind of system has problem, although you are trying to generate this kind of arrangement, which is okay, but practically this is not usable. Practically this is not very successful. You understood the problem here? So this is where actually we go for something called as unity feedback system. What it says basically that yes, you don't take the inverse of the system. You only take a feedback of the output. So let's say you have the plant here, G. This is giving output, say omega. So what you do, you take the feedback of this and there is some reference you compare with that. And whatever error is generated, you just amplify that error and then feed to the system. This is what is the unity feedback system model. In a most simpler manner, this can be done. Now let us see what is happening with our input and output. See, ultimate aim is to have this, more or less, correct? So now what we will have over here, can you suggest? How this will be defined? Yeah, Ashish?
Sir, transfer function, sir.
Hmm.
Kg divided by 1 plus kg.
Yes. So let us simply write what is omega basically. Omega is nothing but kg times of omega star minus omega. Any problem in this? Nothing, right? This is what it is. Correct. And if you simplify, it will come down to what Ashish is suggesting. Omega by omega star is equal to kg by 1 plus kg. So K here is a gain basically. So generally the value of this K is something like 100 or 1000 or something like some big number is there. Okay. Or in total you can say this K into G is like a big number, much bigger than 1. So what we have effectively basically, it is nearly equal to kg by kg, which is actually 1. So we are achieving whatever we wanted to achieve through that inverted transfer function. Here we are achieving the same thing through a simple feedback and a reasonable gain. Could be 10, 100, 1000 depending on what you want to make. Correct? Based on your design. So now if I ask you, is this output dependent on the parameter variation of G? Even if the parameters of G change to, let's say, 0.9 G or 1.1 G, will that affect the output?
No,
No,
sir.
sir.
No, sir.
No, sir.
Right. So this effect of parameter variation is nullified. Is that clear? Fine,
Sir.
right?
Yes.
Yes, Saurabh?
Sir, there should be omega upon omega star now.
Yes, sir. It should be inverse of two.
Which one?
Instead of omega star by omega, it should be omega by omega star.
Output
Correct.
by input.
That is true. That is true. Output by input, yes. That I agree. Should be output by input. Correct? Fine, right? So we have nullified one of the problems, which is parameter variation. Whatever we want, we are able to generate. With even if the gain changes by, let's say, 10%, which is big value. Now, how about the second problem? The noise. So what should happen ideally? Let us say if you have a noise of some of the order of 1 millivolt. At least what you should do, that this should not get amplified. The amplification for this noise should not be there. First condition. Second, as much as possible, the noise should be attenuated. Understanding my point? So in any case, your system should not increase this value of this noise, whatever. Say it could be millivolt or or could be few RPM based on what system you are dealing with. No, the disturbance on speed could be something of the order of few RPM. This is also noise. So whatever quantity is there, whatever noise you are getting on the output, or whatever noise is going into the system, that should definitely not be amplified, and if possible, it should be attenuated. This is what should be there. That's what we want. But is our system able to do that? That we will check now. Okay. So what we have basically, we have omega star, feedback, the gain K, the system G, and we have omega output. Say here we are getting some disturbance D, and then this feedback is taken. Correct? This is within the plant, within the system. We have disturbance D injected somewhere. Now, to see the impact of this disturbance, what we will do, we will keep this input equal to 0. So we are only seeing the effect of this noise getting injected in the system. Now, can you tell how the transfer function or the equation will look like?
1 by 1 plus kg.
Yeah. So if you simply write what is omega, basically the 0 is coming, so minus omega is there, times of okay, so this plus d is coming, correct?
Yes, sir.
This is what it is. Now simply you can write d by omega, or sorry, omega by d is coming out to be 1 by 1 plus kg. Now what is there? We have kg again much higher than 1. So this is equivalent to 1 by kg, which means corresponding to this input d, the omega, whatever is generated by this disturbance, is getting attenuated very, very significantly. This is something like 1 by 1000, 1 by 100, or some bigger number, right? So if there is disturbance of 1 millivolt, say, then this becomes 1 microvolts. So it is attenuated significantly. We are not doing anything additional. We have simply taken a unity feedback system, and that is all. So it is fulfilling our both the conditions. First, it is cancelling any parameter variation, whatever is there. And second, it is attenuating the noise, whatever is injected in the system. So which is why whenever we talk about any system, when we want to have good performance, what we should have is basically a closed loop control. This is the meaning of closed loop control, or this is also known as unity feedback system. So this is what we are trying to achieve in our system, right? Now, let us come back to our system. You have understood why this is important, why closed loop control is important. Now, if we come back to our system, we have power converter plus our DC motor over there. So this is some VG. Then VA is generated where you are subtracting EB. Then you have the first order plant, which is generating IA. And there is this constant C, which is generating torque. Load torque is subtracted. Then the first order mechanical system. We have omega. So EB is basically again coming as a result of omega. So this is what our system is. Now what we should do for this system, we should ideally place a controller somewhere here, right? And we should give some reference, because ultimately our output is omega. So reference should be given as omega. Okay, it will be compared. And this controller should do this job. You understand my point?
Yes, sir.
Correct. This is what it should be. This is some controller which we are putting over here. Now the question is, we should also be careful about what our system or what our controller is going to deal with. There are two systems involved in this. Two first order systems are there. One is basically electrical and another is mechanical. Now, if you see how these transfer functions or how these systems are basically in terms of their time constant. So the time constant for this electrical system is basically LA by RA. And for the mechanical system is J by B. If you compare the values of these time constants, this is something of the order of, let's say, tens of milliseconds, something like that, 10 millisecond or 1 millisecond, something of the order of that. Whereas mechanical system could be, let's say, few seconds to 1 minute or so for bigger systems. That is how big the mechanical system time constant could be. And on the other end, we have a system which is having very small time constants. So kind of we can say that these two time constants are incomparable. We cannot compare these two. this is kind of insignificant compared to this. So if we try to keep a common controller, what we will have, the common controller will basically ignore anything coming on the electrical side and it will simply jump for the mechanical system, which may not be a good design, right? So, which is why what they suggest that why not we control the electrical, so electrical including the power converter as well, electrical system separately and the mechanical system separately. You understand the point? Is that clear?
Yes, sir.
So
Yes, sir.
what we will have basically, let us say if we take the electrical system first, so then what we have including the power converter I am saying, so we have Vref which is multiplied by Vg generating Va. Now we have the back EMF getting subtracted, the first order system, and Ia is generated. So what is the output of the electrical system? Armature current. So we should have a reference for the armature current for the electrical system. So this must be compared. And then the difference whatever is coming over here should be fed into the controller. And that will generate the reference for the power converter and this control can go on. Correct? Fine, right?
Yes, sir.
Yes, sir.
So in effect, what we will have basically, if you see this block, we will have IA star as input and IA as output. So if we ignore the dynamics, just steady state value, these two should be equal. So ultimately, the complete system will look like this. IA tracking the IA reference. Now, once we have achieved this, then we can go for designing the controller for the speed. So what we will have now? So the speed system is basically starting from when we already have IA and then it is multiplied by the constant C, generating the torque. Load torque is subtracted. We have the mechanical system generating omega. Fine. Now here, since the output is omega, so our reference also should be omega. And then this is compared with the speed, the feedback of this output. And the difference is fed to the controller. Now, what this controller will do, how these two things are connected is basically, this is where our current control plant is sitting. So this output generated by the speed controller is nothing but the IA reference. And the output is of course IA. So here in the box, we have the current control loop. You understand the point?
Yes, sir.
This point is
Yes,
clear,
sir.
right?
Yes, sir.
So this whole circle, whatever I have drawn over here, is going into this box. So we are not giving a separate reference for the current, armature current. We are giving only the speed reference, and this reference for the armature current is generated by the speed controller, and then all the operation is happening. Now, if you draw this whole thing together, the complete big block diagram, so we have speed controller over here generating the IA reference. The IA is compared here. Again, we have current controller which is generating Vref. Then we have Vg generating the Va. Eb is subtracted here. Then we have electrical system 1 by Ra plus SLA. And then we have Ia generated, which is multiplied by C, generating the torque. Load torque is subtracted here. Then we have mechanical subsystem, which is generating omega. So this feedback is coming over here. But we also have one feedback which is coming internally from here. And of course, EB is inherently coming as the result of this omega. So this is the complete block diagram. We can say that when we want to control the DC separately excited motor in closed loop control mode, this is what we may have. Now, how to design these controllers or what these controllers are, this we need to understand a little bit, right? We cannot simply put some random controller and we can expect it to give the correct result. We cannot have. So what we should do? We should first understand that how this system is behaving or what we should expect from this system. So let me mark this in one box. This is what we say is that current control loop is coming. And because this is confined within the speed control loop, we call this as inner current control loop. And then whatever we have on the surrounding, that is called outer speed control loop. And please understand, these two controllers, current controller and speed controller, they are dealing with very, very different time constants. One is dealing with the electrical time constant, another is dealing with mechanical time constant. So the properties of these two cannot be same. Properties, I mean, let's say bandwidth or response time, this cannot be same. Actually, when we are having the speed controller on the outer side and the current controller on the inner side, what we should expect that this internal loop must be settled much faster than this outer loop. Ideally speaking, this block, this blue circle, is nothing but this compared to the speed control loop, what we have on the outer side. So this current control loop must be much faster compared to the speed loop. Much faster, I mean, this should settle down. Whatever reference you give, the current should track immediately compared to the speed. If the speed is taking, let's say, 1 millisecond to track, this should track within, say, 0.1 millisecond. You understand my point? This must be followed, because otherwise, if let us say this is taking longer time, if IA is taking longer time and this is not settled before any change happens on this, then this itself will create a big disturbance for this outer loop. And so this will not be valid. Whatever we have written here, IA star is equal to IA. This will not be valid. If it is taking too much time to settle down, then that means this is not one, this is some other dynamics involved here, some other transfer function is there. So we must ensure that the inner control loop is settled much before than the outer control loop to have proper operation of this controller. Understand the point?
Yes, sir.
Yes, sir.
Correct?
Yes.
Any confusion in this? This is critical because this will again come for the induction motor control, PMSM control and all that. So this point you have to understand very clearly. What is the way to design the inner current control loop and outer speed control loop. So the inner loop must be much faster compared to the outer loop. This is the bottom line of having this kind of control. And this kind of control is basically called as cascaded control. We are having one control loop inside the other control loop. So this is what we follow for the motor drive control, and we will learn how to design the controllers. Which controller is suitable, how to design the parameters of that we will see. Now, two things what we are going to use for designing these controllers is, first, we are going to have only linear controllers. So which means P or PI or PID, etc. could be there. And we will use Bode plot as tool to understand the properties of the system, whether it is unstable, stable, or how the dynamic behavior is. These things we will understand through Bode plot. We will also have step response for understanding the behavior. So these tools we are going to use for our system design. Fine. Now, let us go to this thing one by one. We see that what we can have here. So I'm going a little slow today intentionally because it should not become too heavy. This week we have another 2 more classes. So I'm giving you some extra time to absorb all this. Okay, so let us first understand what is linear system. When we are talking about linear control, definitely it is applied for linear systems. So as far as possible, we will try to model our system in a linear manner. No, we will not talk about any non-linearity in the system. We are not dealing with it. If anything is there which is making the system non-linear, we will linearize it through some modes, through some methods. So what is the meaning of linear system? What do you understand by that?
Sir, input and output are related through some linear operators.
Okay, so this is very, very generic, related through some linear operator. So say this is there. So U is basically f of x. Correct? So two properties are there. If you amplify the input by some say parameter alpha, then output is also amplified by alpha. So if f times of alpha x you feed, you will get alpha times of u. This is first property of linear system. Second property is if you have two inputs, say x1 and x2, so f of x1 plus x2 is equal to u1 plus u2, where u1 is f of x1 and u2 is f of x2. These two properties are basically the requirement for the linear system. Correct?
Yes, sir.
So if any system is fulfilling this criteria, then fine, we can call that as linear system, and then all our assumptions, all our designs are valid for that. Correct? Now, little bit I will start on the Bode plot today, and then some more discussion we will have on that side. So what is Bode plot? You all must have learned. So Bode plot basically defines the properties of, let's say, any transfer function or any plant, say GS. So what do we have in this? Basically two plots are there. One is called the magnitude plot and the phase plot. So what is magnitude plot? Basically we take the magnitude in this manner. So 20 log of this magnitude of G. So this is plotted in dB. And here the phase is basically whatever phase this GS is having. So you can plot in degree or radian, whatever. and both are plotted against omega, the frequency. Correct? So with frequency, how the system is going to behave in terms of magnitude and phase, that's what is defined by the Bode plot. So based on this, we can understand how our system is going to behave for a particular input frequency, for a particular disturbance, for a particular input. All these things we can understand from this behavior. And this is plotted on semi-log graph paper. So meaning of semi-log is that this omega is plotted on the logarithmic scale. So if this is omega x-axis, then 0.1 omega and 10 omega are equidistant. This gap is same. That is the meaning of logarithmic scale. Okay, semi-log because only the x-axis is logarithmic. The y-axis is not. Y-axis is as it is, linear scale. Fine. So this is background about Bode plot, which some of you might be knowing already. Now, let us say if I take a general transfer function like this. So how do we plot Bode plot for this? And particularly when I say Bode plot, I am talking about asymptotic Bode plot. The reason being this is simple and yet it carries most of the information what is needed from our system. So almost accurate, but it is very, very simple to plot. So that is why we will follow this. Now how to plot the asymptotic Bode plot for these, let's say this transfer function. Okay, so quickly I will tell how to get the magnitude and phase approximately and then how to plot, and then some 1 or 2 examples we can see tomorrow. So first is, let's say we talk about the magnitude plot. What we have basically, we are trying to have 20 log of G. So this means 20 log of this whatever expression we have, magnitude of K, and this magnitude of numerator will be simply S square by, sorry, so this becomes omega. And divided by whatever denominator we have. Correct. So anyway, magnitude is taken. So this is just bracket. Now, because this is log, so all this numerator denominator can be opened in simpler arithmetic manner. So this can be written as 20 log K plus 20 log of minus 20 log of. Correct. This all you know, right? Now, just a quick review I will give. So here this is constant. It is not dependent on omega. There is no problem in that at all. If you plot on the graph paper, it will be a constant line with any omega, 20 log K. Now, if you talk about any this term or this term, so what is associated with 0 or pole, then what we have basically for asymptotic Bode plot, we can make approximation for values of omega which are very far from omega z, whether very small or very large. So if I have to write 20 log of omega z square, so I can say that this value is, say, for example, 0 when omega is very, very smaller than omega z. Correct? If omega is very, very small, this number is very, very small, so log 1 is 0. And then if omega is very, very large compared to omega z, then how it is behaving? It is basically behaving like 20 log of omega by omega z. Isn't it? That's the approximation. So similarly for this pole also we can write in this manner. Now, what does this say? The asymptotic Bode plot, what does it say is that if you have to plot the magnitude against omega, So it will basically, because initial value is 0, so we are only talking about this, say G1, you can say 1 plus S by omega Z. For this part only we are talking about. So it will start, say omega Z is here. So it will start from 0, and at omega Z it will start going up. At what rate?
20 dB per decade.
Yes. But why 20 dB per decade? What is so special about 20?
Sir, we are plotting in semi-log, so
No, that is fine, semi-log, but how this number is coming? So you can see from here, whatever approximation we have taken, this 20 log omega by omega Z. Say, I ask you, if this value is some constant, say K1, then what is the value at some 10 omega? 20 log of 10 omega by omega Z. So what your answer would be?
20 plus K1.
Yes, exactly. So this can be separated out as 20 log 10 plus 20 log of omega by omega Z, which is K. So this is nothing but coming as 20 plus K1. So we have moved the frequency by 10 times, 1 decade, and we have got the change of 20. So that is how this 20 decibel per decade comes. So this is true for any first order system, whether it is 0 or pole. So either this may become plus 20, or for the pole it may become minus 20 dB per decade. Correct? Now just a quick thing for the phase, and then tomorrow I will start this again. So how do you get the phase of this transfer function? So you have angle to be taken for this. Basically, the constant term associated with any transfer function doesn't have any phase. It is 0. So you can separate this out, everything. So phase of K plus, you can say phase of 1 plus S by omega Z minus whatever phase is associated by 1 plus S by omega. This can be simply separated out like this. And then this phase is basically 0. And phase associated with any 0 or pole can be written as tan inverse of omega by omega Z. And for the pole it could be tan inverse omega by omega p. So this is the phase of this transfer function, which is having these three terms. Now, how do we approximate this? Again, generally I have seen students going for MATLAB and plotting the exact phase what it is coming. No, when I am talking about asymptotic Bode plot, we are dealing with only straight lines. We are not dealing with the curves. So what we have basically tan inverse of omega by omega x, let us say, any corner frequency. I am not saying it is 0 or pole, what it is. How do you approximate this? If let us say one extreme condition I have that omega is very, very small compared to omega x. So what will be the value of this phase?
0 degree.
0, because this is very small. But when I say very, very small, what is the number I am looking for? This is something like omega is of the order of 0.1 omega x or less. So this is less than or equal to this. For this time period, for this frequency range, this will behave like a 0 phase. And if I say that omega is very, very large than omega z, then what will be the value?
90.
90 degree.
So here again, when I am saying very, very greater than, omega is greater than or equal to 10 times of omega z. That's the approximation. And in the middle, what we have? 45 degree when omega is equal to omega x. There is no problem in that. So we start from here tomorrow and complete the Bode plot and other design parameters. Okay. So any quick questions you may ask, otherwise we will stop the class.